Expo 2020. This is a terminology leading practices stream, and right now our presentation is going to be from Brian Carlsen from West Coast Informatics. Brian, please proceed.
Thank you, Allison. All right, welcome everybody. So this is a session about a project that we did to do a kind of automated mapping approach of SNOMED to ICD11, which is of course an evolving thing. But this was an effort to see how far we could get using various sort of advanced mechanisms. This involved the same scope as the SNOMED-to-ICD10 maps, so SNOMED clinical finding situation event concepts mapped to ICD11 STEM codes. We kept the extension codes out of scope for this work, as well as any considerations around post-coordination for the moment. We began with a set of frequently used ICD-10 codes provided by member countries to SNOMED International. Some of these were proper, true ICD-10 codes themselves, and some were derivatives in, national custom extensions of ICD, like ICD-10-CM in the US. We took these codes, mapped them essentially up to real ICD-11 codes as best as we could. I'm sorry, ICD-10 codes. Then we computed all the descendants of all of those things, and then used the WHO provided ICD10-11 maps to attempt to compute a scope of ICD-11 codes that would correspond to that set of ICD-10 codes as our target scope for this project. That yielded about 13,000 ICD-11 codes. Then we went back and took the ICD-10 maps and found all of the SNOMED concepts mapped to that original set of ICD-10 codes, and put them in scope for the purpose of the source scope of this mapping project. So essentially mapping from about 84,000 SNOMED concepts to 13,500 ICD-11 codes. For this project, we used a variety of machine learning models that we built and algorithms to produce essentially an automated SNOMED to ICD-11 map that was human reviewed as a mechanism to qualify it. And finished the process using an iterative approach of essentially human mapping, regeneration of the algorithm, comparison against the human maps to compute precision and recall, identification of categories of things that we could use to either expand our ability to find the gold standard codes or in fact to have the algorithm pick them. So to do this, we thought about what are all the things about SNOMED that we could use to leverage ability to find connections to ICD-11 and then sort of value those connections. So obvious things are the defining relationships, which provide explicit information like body parts and other things, the hierarchy information, the hierarchy itself, so that we could leverage both things like the SNOMED to ICD-10 maps of parent or ancestor concepts, so the concept we were considering, or leverage the algorithm's choices for SNOMED to ICD-11 maps generated prior to a concept being considered. So essentially try to leverage the generalization and specification mechanisms in SNOMED to bridge the differences of how that works in ICD-11. It turns out the semantic tags are potentially useful for the scope of things. Situations, disorders, straight findings, events all have sort of slightly different things about how they get mapped. And so, within the scope of that, there could be different approaches and different rules built around those things. Obviously, the descriptions, the names of the SNOMED concept themselves are key to finding connections, as well as information about the term types and other aspects of those things. We included some synonyms that were generated to also expand the scope of how we could match SNOMED to ICD-11. And then the other key thing is the SNOMED to ICD-10 and SNOMED to ICD-10-CM maps we could use as a means to find our way through the WHO provided ICD-10-11 maps to an ICD-11 concept. So on the other side, we've got features of ICD-11, very similar things. ICD-11 starts with the notion of chapters. This example here is a chapter 20 concept. Knowing that it's chapter 20 is part of what we built into this as a means of both identifying and qualifying things. ICD-11 has its own bit of a hierarchy too, so we could do things like match to higher in the hierarchy and understand that the target code would be one of the leaf node descendants of those things. ICD-11, like ICD-10, has index entries, so there are provided an additional series of names that also should map to these things, often considered inclusion, so explicit conditions that wind up aligning with other categories. So that's very helpful in bridging this gap between specificity in SNOMED and the specificity in ICD11. And then in this case, we can use SNOMED to get to ICD10 or 10cm, and then we can use what was provided with ICD11 to get from ICD10 or ICD10cm to ICD11. One of the things we had limited access to for this project is the exclusion information. So there is some limited exclusion information available in the data resources we had, but not really comprehensively enough to build in any sort of comprehensive way. So that would be a kind of future thing that we could take a look at. To get there, we built 4 machine learning models. The first one we call the chapter prediction model. It essentially was trained off of the SNOMED-to-ICD10 maps and the names of ICD10 and the names of ICD11 concepts themselves, where we did an alignment between the ICD10 and ICD11 chapters to say, given a SNOMED string, it essentially aligns ultimately with this ICD11 chapter via the ICD10 map. So the model was built off of text and word embedding text models, and essentially takes a name of a concept and predicts the ICD11 chapter or chapters that may have codes, corresponding codes. It's a multi-class model, so it can predict multiple chapters, which is then an indicator or a suggestion that that SNOMED concept may actually have multiple stem code maps in the corresponding ICD11 terminology. Second model, residual prediction model, is another classification model, essentially built to predict from a text string whether or not this thing would wind up with an ICD11 specified code or an other code or an unspecified code. Similarly to the chapter prediction model, this was trained on the SNOMED to ICD10 maps, as well as the actual names in ICD10 and ICD11. The way in which other and specified and unspecified exactly work changes from ICD10 to 11, or at least the things that wind up being classified into those different categories is slightly different, but we felt that this would be a good model as a tiebreaker where otherwise all other information is kind of equally valid predicting between 2 options. We could use this as a means to make a final decision. We built an NLP model for this. This is something we'd like to extend further in the future, and essentially, built this as a body part identification model. So in both SNOMED and ICD10, ICD11, essentially what it does is we pre-annotated some strings by identifying body parts using matches to SNOMED, and then trained a model that would take an arbitrary string and predict text within that string that represents a body part. We align those body parts with SNOMED body part concepts, and then leverage additionally the SNOMED finding site relationships and things like that. So the goal of this model is essentially to say whether or not a concept on the SNOMED side or the ICD11 side has a body part, and then we can determine whether those body parts are compatible. And the fourth is word embedding mechanism, search engine. So the idea here is to train, we did actually use pre-trained word vectors, but the technology is to train mathematical vectors on large corpuses of text, in this case PubMed and Mimic free notes, to create vectors representing all of the sort of words in the biomedical space. And the idea then is that we can create a kind of sentence vector that represents each ICD11 name. And given a SNOMED name, we can compute a sentence vector and then use a vector similarity mechanism to identify essentially close semantic matches across these terminologies and across the way that language works among these things. Our algorithm essentially took an approach of using 3 different phases. Phase 1 was to fruitfully generate potential candidates between SNOMED and ICD11. So find pathways between our source terminology and our target terminology, and generate potential connections. So the mechanisms we use for this are things you would imagine, high quality lexical matches. So just using a standard kind of text indexing lookup mechanism, see which things just match very well. The word embedding search engine discussed on the previous slide is a mechanism to find connections that aren't necessarily exactly lexically oriented, but leverage similarities in the overall semantic space of how words get used near each other. And we'll show an example of that later. Third thing, of course, we could do the crosswalk. So take SNOMED, walk to ICD10 or ICD10-CM codes, then align those things with the ICD11, WHO provided ICD10 to 11 maps, and essentially crosswalk to a range of potential ICD11 codes that roughly correspond with the original ICD10 code maps. We also use mechanisms to inherit candidate maps from parents. So by producing the map in SNOMED hierarchy sort order, every time we encounter a concept, its parent concepts have already been mapped, which enables us to then leverage the information about that work done to apply, identify potential candidates and actually try to also rank them based off of that. If all of these other mechanisms fail, we built this chapter prediction model. So we have, if nothing else, worst case scenario, the opportunity to consider every possible ICD11 code that's in scope in that chapter as a potential target. And then use a variety of rules to essentially take all of the maps that were generated in the previous steps and then sort of expand the space around them to include potential other things. The most important of these mechanisms was to say, every time we predicted a potential match to a Y or a Z code, so an other or unspecified thing, also take the other one if it wasn't already in scope. So reconsider whether everything is other or unspecified if those are potential targets. Second part of the process is essentially one by one, take each of those SNOMED to ICD11 connections and assess the compatibility of them and rank and measure those things in a variety of different ways. And then finally, take all of those compatibility measures and essentially compute what we want to do and where we want to go and what the right answer is. So now we'll go into a little detail. So here's some examples of each of the kind of stages of the phase 1 candidate generation. So high quality lexical match. Here we've got viralization matched to adrenogenital disorders. You might say, that's not a lexical match, but in fact, this concept 5A71.Z does have an index entry that is a very good quality match to the SNOMED concept name on the left. And so that is why this gets picked up as a lexical match. The second case, you can see how these are close to each other. Central nervous system is compatible lexically, it's a lexical similarity, but ependymoma and glioma are very different words lexically, but in fact, one is a form, an ependymoma is a kind of glioma. So this is a connection that's able to be made by this word vector similarity that otherwise wouldn't be found by pure lexical means. Third is an example of crosswalk through the ICD10-11 map. So delusion of heart disease syndrome becomes delusional disorder. This may not, in fact, be the correct maps. This is an example of a candidate that was generated based off of walking of the maps. Sometimes the map crosswalking is very helpful and yields a small number of high quality choices. Sometimes it maps to a code that has dozens of possible choices in ICD11 and is kind of less useful at precision at least, but the candidate generation is still quite good. Like we said earlier, it's possible as well to take previously mapped situations from the parent hierarchy in SNOMED and apply them in this case. So here, the case of a flaccid monopeglia of upper limb, its parent would be something more generic, which would map to other specified paralytic symptoms. So this is a case where that more general code that comes from the parent mapping could be considered also. There's a point at which more specific codes stop being used and less specific codes stop being used as you go down the hierarchy, and more specific codes wind up being used. But it's not always clear exactly where that happens, so being able to consider the more general cases is useful and valuable. And then finally, here's a case of just a chapter prediction link. This pneumonia due to H1N1 just links to other specified, because the C chapter is the one that's in scope for the prediction of the SNOMED concept on the left. And finally, the example on the bottom, LD7Z was chosen as a candidate by prior steps for this concept on the left, chromosomal alterations of group G and Y. And because we considered a Z, this expansion of the scope also considers Y candidates, other specified chromosomal anomalies here. So those are examples of kind of how each thing kind of gets to the answer. So once we have a set of candidates, we go through and one by one assess the compatibility of the SNOMED concept and the ICD11 code in this case. And these are 6 important measures we use. First one, the name score, is essentially a measure of the lexical similarity of all of the names that are associated with the SNOMED concept and all of the names associated with the ICD11 concept. And we basically find which is the best match and put a score on that between 0 and 1. The residual score is an outcome of this ML model we discussed earlier. So there's a prediction of the SNOMED concept of whether it's other unspecified or specified. And if the corresponding ICD11 code candidate matches the prediction of the model, it essentially gets the score that the model predicts. Otherwise, it gets a diminished score for being a non-match. Then we do body part compatibility assessment. So if the SNOMED concept has a body part and the ICD11 concept has a body part, and those body parts are the same, or if the SNOMED one is less specific than the ICD one, or if the SNOMED one says one thing and the ICD one says A or B or C, and it matches, then that's a kind of compatibility. Whereas if they talk about different body parts, or one talks about a body part and the other one doesn't, those things get downgraded. And then the situation where neither talks about a body part is also considered a match, since they both don't refer to body parts. Lexical incompatibility isn't a score, but it's a mechanism by which we can essentially override potential matches based on known things that just never go together. Like a normal thing and an abnormal thing don't go together. A primary and secondary things don't go together. Something that's benign doesn't go with something that's malignant or metastatic. And there, in cancer especially, there's all kinds of variations of this. So we kind of built a mechanism to fine tune based on lexical incompatibility. This turns out to be very useful for tuning down the candidates to the right answer. We use a chapter score. So is the predicted ICD11 code, is this candidate ICD11 code in the predicted chapter that we would expect for the given SNOMED concept? And there's a slight variation in score. This is another tiebreaker that we use to differentiate between potential candidate matches. And finally, is the choice compatible with the choice that was made for the parent? So because we process them in hierarchy order, by the time we encounter a concept, its parents will have already been mapped and a correct best match would have already been chosen. So we can assess whether or not the best match for the child is compatible, or this candidate is compatible with the best match of the parent, which then gives it a little bit of a boost for consideration. Then we take these compatibility assessments and we essentially produce the answer. So we compute a confidence score for each SNOMED to ICD11 pair. We determine for that set, that case of all of the SNOMED candidates, which one has the maximum confidence. The highest confidence thing is the best, considered the best match. And then we also compute a difficulty level of easy, medium, or difficult, kind of based on the maximum score value, how close it is to 1, the number of potential candidates that were involved, and the distribution of scores. So things with standout winners, where there's a distribution curve that drops very quickly, that tends towards easy, and where the scores are more flat and you have many resulting candidates that all have kind of about the same high score, that tends towards more difficult. And this easy, medium, difficult is really a measure intended to drive a workflow. So the thesis is that things that are marked as easy with high quality answers require less review. The answer is generally going to be in the top 2 suggestions. With medium, it gets a little bit lower than that, and things with difficult may predict the right answer in situations, but they probably should all be actually manually reviewed. So we compute the best match and what we consider an almost match, which is either the second best or a best within 10%. Those are kind of the measures that we're playing around with. The goal of this whole process with respect to this difficulty and everything is to try to get to a point where about 60% of what we compute winds up coming out as easy, and these things should ultimately have the right answers very frequently, ideally above 90% of the time. Then the sort of half that amount more as medium cases. Generally, these should be right also. At least 50% of the time we want these to be right. The top answer be right, and then the answer be somewhere in the top set of things, frequently. And then difficult things, which sort of should be a small set, and then these really do require review. We don't have any expectations about how this would all kind of work out. All right, so we've got a few simple examples. So here's an example that is the result of a lexical match. So hyperpituitarism becomes hyperfunctionality of pituitary gland. And then here you can see some details of the algorithm. This was assessed medium level difficulty. 10 candidates were predicted a chapter 5 answer. The top one here was found via best lexical, 5A60.Z, gets a score of 91%. It's a very good quality match. You can see the second one here, they go in sort of rank order, is hypopituitarism, which is kind of the opposite of hyper, right? But semantic similarity puts it in scope, and so that's why it winds up near the top here, because it's semantically very close. And then this trails off with sort of other examples. This is a clear case where we are fairly confident of the right answer, and it's found via a very high quality lexical match. Here's another case that comes from the embedding. So while these things do have lexical similarities, the nature of these strings essentially doesn't produce a high enough lexical quality score to get considered from the straightforward approach, but it is found by the embedding algorithm. Carcinoma in situ of lip, oral cavity, or pharynx is the top embedding choice and winds up having a very good score also. This ranks as medium, even though it has a small number of candidates, because the max score wasn't quite high enough to push it over the edge. But this is probably the right answer. And then number 3, we've got a case that came through essentially the ICD11 maps. Here you can see there's very little lexical or even word similarity semantic comparison between hypervitaminosis and other specified nutrient excesses. But this is a pretty clear map through from SNOMED to ICD10 to ICD11 that kind of puts us pretty much in the right space, and we essentially wind up with either a choice between the other or unspecified examples. And in the end, the algorithm picks other instead of unspecified because this does actually have specification. Okay, so just a quick overall results. This is from about a week ago. We're still working on this and continue to tune it. But recall is essentially our ability to predict the gold answer in the set of candidates, and precision is our ability to get the right answer. So for the easy set, here we go, higher scores overall, and we're pushing these above 90, and precision also as high as we can get it, ideally above 90. And the point of this slide is essentially to say this approach is valuable. While it may not always produce the right answer completely algorithmically, it actually puts in front of a potential editor a much narrower range of candidates, and the workflow process surrounding this could be significantly more efficient and effective than just trying to do this from scratch with manual editing, especially if you wanted to do dual review, because you could limit dual review to the difficult cases. The easy cases would be mostly correct and just a simple choice between the top 2 answers, and you could very quickly get through human review of the majority of the map. Okay, so there's some things that we can do forward. You know, we could improve the NLP model. We could do a little bit more with classification models, because there are things like histories of procedures that would be treated a little differently. You know, we could focus the human review at the higher level concepts because of that inheritance mechanism. Each edit effectively has more power and more value. We could do more to deal with the way that generalization works in SNOMED versus ICD11, because other and unspecified sit at the same level, where in SNOMED, other would be more specific and unspecified would be less specific. So, you know, we're learning through that. The ultimate long-term amazing thing would be to have an active learning model where you could essentially have a model that learned as you produced answers, and it would train the predictions on future answers. So as you went through, it would get better and better. Okay, so let us know if you have questions, and send us an email if you want to know more.
Great, thank you, Brian. I'd also encourage delegates, if you're attending live, especially to visit the West Coast Informatics booth at our on our exhibit hall. If you just give us a minute, please, for those attending live to switch over to the live question and answer, and Brian will be able to answer some questions.
Yes, thank you.
Thank you.
Thank you, Brian, for that very interesting presentation. This is the live question and answer portion of the presentation. My name is Jim Case. I'm with SNOMED International, and we have a few questions in the question box. To what extent is your algorithm useful in mapping SNOMED to other classifications outside of ICD11? And how are large parts of the algorithm possible to use in other languages than English?
Yeah, I think the generalizability question is an easy one to answer. The techniques that we used are applicable to other situations. I think the fine-tuning is really where you get into the very specific aspects of, in this case, let's say exactly how ICD11 coding works, which wouldn't apply to other terminologies. But a lot of the sort of bulk techniques are specifically intended to be generalizable, and we are in fact deploying this approach to solve other mapping problems currently. Maybe we'll get a chance to talk about it in the future. And other languages, I would say, you know, the main thing about other languages is that the resources that are available for things like normalization and word embeddings and stuff like that are more limited. So there's probably just more curation of targeted resources for other languages, it would be needed, but I think the same approaches could work very similarly.
Thank you. And the next question, are there additional types of data mappings that would materially increase the F-score if they were available or created?
Sure. There is a report that we wrote up about this. You can actually find it in our booth, but then also we'll make a link available. It's a sort of public. And, you know, we talk about some ways to improve this approach. And I think especially by doing some more targeted NLP work to really break down all the features of this string and have those things bound to SNOMED concepts in particular ways, like resources like that. So essentially, if we could take ICD11 and reinterpret it in the context of how SNOMED views the world, then there would be a very straightforward alignment that was not just sort of purely lexical, but more structural. And I think if there were other files available, other maps too, anything that mapped to ICD11 would certainly help. But it's new enough, that's not really the case yet.
Our next question, first of all, says, great talk. How do you handle more specific SNOMED concepts, that is, descendants of those that get a lexical mapping?
Well, I mean, there's two ways to leverage that information. One is to say, certainly, if I'm a more specific concept, I should consider what my parent was mapped to as a possible candidate for myself. This is especially true if the parent concept has sort of reached a maximum level of specificity in ICD11. You would expect every descendant concept of that corresponding SNOMED thing to have the same ICD11 code. And the other way is effectively to say, in those situations where you're close to that line of the unspecified versus other things, you know, is there a compatibility? Do I jump from, you know, you wouldn't expect your parent to be an other something and then the child to be an unspecified thing. That wouldn't make sense, right? So that's sort of the approach, is both generation of potential candidates, but also qualifying of the candidates that you find by other means.
Thank you. Our next question, are the outputs of your fabulous work available for others to see and use? Are they published? And I ask because I'm currently manually trying to map pediatric SNOMED-CT codes to ICD11.
Yes, so there is basically all of the outcomes of this project were put in a public Google Drive folder. It's not published in the sense of being a, you know, peer-reviewed paper kind of thing. Well, not at the moment anyway. But everything that we did is available for use. I'm not sure what the best way to communicate what the URL for that is. I think maybe Rory can help with that, or you can come to the booth. We have a virtual booth, and we can chat us, and we'll give you, you know, information about that.
Our next question is from Rory. Having worked with the tighter scope of 10,000 ICD codes, do you think taking the whole scope of ICD11 MMS would generate too much noise? And a follow-on question to that, how would this compare if you were trying to do this to the foundation layer of ICD11?
Wow, okay, so the first question I would say, I think, you know, given our experience with this, trying to work with a smaller set of downscoped concepts to begin with actually made things more complicated, because we had to sort of work around everything. And in the end, the map that we produced wound up having a bunch of effectively out of scope ICD11 codes in it, because otherwise, if we were forcing the algorithm to pick something in scope, it would have picked the wrong answer. And you know, you consider we had 84,000 concepts in scope for this project. The whole scope of the MMS is effectively the same as ICD10 scope, which is finding situations and events, some 130,000 concepts. So opening it up to everything doesn't even make the pool 100% bigger. It's not even twice as many codes to map. So I don't think there would be significantly more noise. I think by virtue of being able to fully leverage all the hierarchies, it would actually probably be better. And expanding it to the whole foundation, I have spent a lot of time really kind of assessing ICD11 MMS and the nature of the language that's used and sort of how it aligns and works with SNOMED. So, I mean, I think it's certainly possible. It's that it would come with all kinds of other challenges just around how those content areas are represented differently or misaligned in their own special ways with respect to how SNOMED works. But it's probably worth doing or looking into.
And our last question is, do you envision being able to extend this approach to map post-coordinated SNOMED-CT expressions to reference terminologies?
Wow, that is a great question. I was, in an answer to one of the earlier questions, I was sort of alluding to this idea of, using more targeted NLP to kind of break out the different pieces of, the names, the ICD11, essentially try to use NLP to invent a concept definition for the ICD11 thing. I think going down that approach and doing this kind of lexical and structural alignment with pieces of the whole things is very similar to that. So effectively, I think you could wind up using the similar kind of approaches to align post-coordinated expressions. And ultimately, there is a post-coordination syntax in ICD11, and that was out of scope for this project, but the next level would be to actually do the post-coordination with the body parts and the cancer types and all the other aspects of post-coordination that ICD11 supports, which is more mapping to a post-coordinated expression, but the same thing could be done in reverse.
Thank you. Unfortunately, we're out of time. I would recommend that people that have additional questions for Brian contact him directly. And thank you all for attending this presentation.